So when I was asked to give a series of lectures about type 3 approach to surfactants, so I asked myself whether I should talk about the Tomita-Takesaki theories, those serious type 3 things. And I thought that the answer should be no. What you really want to hear is not a really type 3 approach, but sector approach, right? Yeah. So, well, actually, so the sector approach was developed in the, its origin was in quantum field theory, algebraic approach of the quantum field theory. And once you admit just one thing about the type 3 factors, namely, so any two non-zero projections of a type 3 factor equivalent in the sense of Murray von Neumann, then that's it. You don't really need to use other deep stuff like Tomita-Takesaki theory of type 3 factors. And in a sense, so the theory, sector theory works even for sister algebras once you have that property. Namely, so for example, for the Kunz algebra O2, it's a famous sister algebra, not von Neumann algebra. It's a purely infinite sister algebra. And it's known that the K0 of the Kunz algebra O2 is trivial, meaning that every non-zero projections are mutually equivalent. And the sector theory works perfectly for O2. So I decided to, at least at the beginning, start with a more general setting, say sister algebra setting. Then I don't really need, I cannot really use Tomita-Takesaki theories. I don't need to explain that. So Born introduced a notion of index for surfactors of type 2-1 factor. And you've already seen that trace preserving conditional expectation plays a crucial role. So, but when you start with inclusion factors, type 3 factors, say, then there's no trace. Then what can you do? Well, you have to assume something from the beginning. That's the existence of conditional expectations. Let L and B be sister algebras. So I start with sister algebras. Then positive linear map. Positive linear map E is a conditional expectation. If, so by definition, it's okay. So B is a subalgebra of A. So it's A is a BB bimodule, and say E should be a BB bimodule map. So namely, so you have this property. For B1, B2 in B, and A in capital A. And so since I already assumed that this is positive mass, so it's unitary enough. So this E preserves the unit. So this is the definition of the general conditional expectation. You don't need to assume the existence of trace then. And by the way, it's well known that Miyama 7, so this is the same as is a norm 1 projection in Banach space theory. But it's deep several. Let's take this as our definition of the conditional expectation.
U1 equals 1 follows from the bimodule property? Because
it's a positive map. Positive map, and it's unitary, so it's normal, always normal.
No, in that if you just put
no, U1 of 1 would be a positive. I don't function with some element of the equation.
from that point to see that U1 is an identity.
What the question?
No, no, no. I thought E1 equals 1 was a consequence of bimodule property.
Not really. No.
1 times E1.
If you take A equal to 1 and B2 equal to B, don't you find that E of B equal to
That E restricted to A is identity, that follows.
only that it is
Wait. No. No, still.
only on the range of on E of B it is identity.
Oh, this is a no.
Yeah, okay.
So if you consider multiple of E, still it is a BB bimodule map, but it's not unitary. Yeah. Anyway, so let me give you two easy examples. So let's G be a finite group. Let's consider G action. Then, so you take the average over G in the following sense. So you have a G action here. So you consider this map. Then this is a map from from A to the fixed point algebra, which already appeared in Bond's talk. Then E the conditional expectation. It's easy to see. It's easy to see that this is a positive map. It's a linear combination, positive, convex combination of positive map. So it's positive, and it's unitary. Okay, convex combination of unitary map. It's unitary, and yes, it's clear. It's BB bimodule. Okay. So this is a typical example, and let me give you another example, which is kind of dual of this situation.
I suppose with B equal to the fixed point.
Yes. B.
Not AG.
So let's consider diverse situations. That's a cross product. So still alpha is G action. Then you can produce a new sister algebra or von Neumann algebra or finite group. It doesn't matter. So this is the sister algebra generated by A and a copy of the regular representation. So this is a copy of regular representation. Satisfy the following condition. So this is a universal sister algebra satisfying with generators and relations. This is a cross product. Then, so by definition, any element here have expansion, unique expansions. Sometimes it's called a Fourier expansion. Here xg is in A. Then you can consider this map. So sending this to this element. So let's call this map, say, E1. Then this is again a conditional expectation. So E1 is a conditional expectation. So again, it's easy to see that E1 satisfies these conditions. Right. So these are typical examples. And in a sense, E and E1 are dual to each other. I'll explain what it really means. Right. So let me give you a reason. Okay, let's consider this situation. So E is given. So A and B are sister algebras. E, B is a sister subalgebra of A, and they share the common unit. And A is a conditional expectation. Then, so we say that E is of index finite type. If there exists a finite subset, U1, U2 to Un, in A, satisfying the following properties, that for any x has the following expansion. And since A is a C-star algebra and E is a star map, so if you take the star of this equation, then you get another equation automatically. So whenever E has such a system, such an element, then you say that E is of index finite type, and actually you call this a basis. This is basis. Strictly speaking, I should say that it's basis of A over B with respect to E. I should say something like that, but I just say that this is a basis for E. Or strictly speaking, I should say Kim-Snapov basis. Right. Then, actually, well, probably it's, so Bond is not here. So if he were here, then he would say that it's not fair to assume the existence of basis from the beginning. But, well, actually, I can talk about the index of conditional expectation of a type 3 factor, without referring to this basis, but this is the easiest way to get basic extension, well, index, basic extension, and so on, algebraic construction. So let me assume the existence of basis from the beginning. So then, okay, one easy fact about this basis is the following. So this number are not really a number, it's an element of the C-star algebra A. So this is always belongs to the center of A. And in fact, it does not depend on the choice of UI. So the definition of this term of index finite type is just the existence of one basis. And in general, so there are many different bases for one conditional expectation.
Misaki?
Yes?
So, sorry, can you just briefly, for those two examples, I can imagine the basis for one of them would be something like the lambda g's or something.
Yeah, yes.
And what's the one for the top one?
Well,
Is there a nice...
in general, actually the top one doesn't have a basis in general. When A and B are factors and alpha, well, A and B are factors, then there exist basis. But this is okay. This is really nice base. But for that, then that's just the existence. You can show the existence.
But you can show the existence.
But
So
you don't really have a canonical basis in that case situation. And for general C-star algebra, then actually, so there is an example where, this E doesn't have a basis. It's related to the freeness of the action for C-star algebra. It's very subtle. Right.
So the bottom, sorry, just so that I've got this right. So the bottom example, E is always a finite type.
Right.
But the top one, not necessarily.
It depends on the property of alpha.
Of alpha.
For general This is the algebra. For factors, it's okay. Right. So this is a statement, and it's really easy computations. Well, this is a. Well, let me prove it. It's really easy computation. So assume there is another basis. Assume this is also a basis. Then, so let's try to compute this. Yes, we want to know this does not depend on the choice of this. But well, we showed so this statement contains actually two statements. First, this is in the center, and the second one is that this doesn't depend on the choice. So let's try to prove the two statements simultaneously. So we compute this by expanding this part using Vj. Okay. So for that we use this. Xi Vj. Yes, Vj stuff. Right. Now, so I should put something here. Now I change the order of summation here. And here I use something wrong. Star. Yes. Then I use the basis property of UI here. Then I end up with yes, this. Right. So you just look at the first term and the last term. If you put x equal to 1, then it means that it gives you that, okay, this summation is the same as that summation here. So this element doesn't depend on the choice of the basis. And once you know that, then this equality means that this summation is in the center of A. Okay. So it's a really easy computation. And actually, the idea was actually, I think it's well, it's I should say Pimson-Popper, and also the idea of Watatani is that to define an index for general inclusion, then let's do this. So this number. So we call this the index of E. Watatani. So W means, well, so Watatani proposed that to define the index of general inclusion by using the basis in this way. So I put W. And I have a few remarks, of course. So when A and B, say A and B are two unfactored, and E is a trace-preserving conditional expectation, then this, well, first of all, so this is the central element. So when A is a factor, then it's scalar. Then this definition, of course, coincides with Bond's original definition. And first of all, I should show that there exists a basis, but that's what Pimson and Popper did.
What is Mn?
Oh, sorry. Okay. So Pim's and Popper show that there is always a basis, and this number coincides with Jones index. And yes, actually already Zeph this asked me about this.
This is only the finite index case.
So what?
This is only the finite index case.
Yeah.
This is
This is a finite index.
or it is not defined. No, it is under the assumption that the index of B in A is finite.
Of course, yeah. So you can relax this condition a little bit. If you allow a series of elements. So this is just a final set in the definition, but if you allow a series of definitions, then yeah, sometimes you get a basis in the case of infinite index in the usual sense. Yeah. In that case, this number is infinite. Right. So in this example, in this case, then it's clear that this is a basis. This is a basis. And the index, in this sense, in this sense, is this number. And this is nothing but a cardinality of Z. Right. And they've already asked, but this situation is a bit subtle. But when A and B are factors, then there is a basis. Using the facts that actually, so this action is a second dual action of something, then you get a basis. Again, you get the same number for the index. Right. So this is one way of defining an index for general case, but there is another way. That's what Pims and Popper proposed. So I'll mention it briefly. Right. So here's another easy lemma. So if E is a conditional expectation from A to B and where is the basis, then you have this inequality. So this one. So since this is just a central element, take norm and identity. So you regard this as a map, linear map from A to A itself. B is a subalgebra of A, so you can regard E as a map from A to A. So it makes sense. Then, actually, this is a positive map. That's what Pims and Popper first showed. Actually, this is also easy and nice argument. So to get used to basis, well, argument with basis, then I think it's nice to have C with proof. So in this case, how can I show this? So let's assume X is an element of A, then we have the following expansion. Yes. So every positive element of A can be written as an XX star. So let's compute this. And here, you have a nice matrix, operator matrix. So So let's consider this matrix, operator matrix first. So this is in here.
The middle term should be changed from UA star UJ.
Ah, right. Something. Yes, this is the right order. Yeah, this is the right order. Right. So let's consider this matrix. Then here, what appears here is that okay. Right? Yes. So if you consider the ij component of this matrix, V star B, then this is nothing but ui star j. So let's compute the other product. V star. Okay. Let me put it here. Star. Then this is nothing but ui star. So this is the index. Right. So this computation shows that the norm of this matrix here. Yes. The norm of this matrix is nothing but the index. Of E. And since this is a clearly positive matrix, so we have this thing called times identity. So using this inequality, and in general, you cannot really reverse them, but say in a good situation like when A and B are, say, simple sister algebras, or when A and B are factors. Then, so if this number is finite, then so there is a basis, this basis, and these two numbers coincide. Equal. Well, in these two cases, then this is not well. So then the center of A is trivial. So this is a scalar. So the two numbers coincide. Right.
So you don't get an implies in the.
What?
You mean if the principal of our index is finite, then the other thing.
Okay, all right. I should write it this way. Yeah. So under either this condition or that condition, then if the probabilistic index is finite, then it implies the equidistance of basis, and the two numbers coincide. Right. And this requires a proof. It's not really simple, but I skip it. It's not a real point of this series of lectures.
What does P stand for?
P probabilistic or P-Snapper? Whichever. What? PPP, yeah. So to make Spring happy, I should put P.
By factors, you mean two factors or any?
Any. Actually, 2-1 factor is automatically sister algebra. Actually, factor is also simple sister algebra, but 2 infinity or B of H are not simple sister algebra, but still. That's it.
So that's the same thing as saying if the index is infinite, there's none. There's no Pipson probable constant, none. Is it there's two in the Pipson problem? There's two directions. There's the hard one, and the easy one. Is that the easy one?
So So the easy one is with what I already proved, or
So that's
I proved. So equidistance of basis implies Pym-Snapova inequality.
So for C star algebra, that must require.
But for general C star algebra, or general, say, von Neumann algebra, Pym-Snapova inequality does not assure the equidistance of finite basis. If you allow a sequence, then the equidistance. Right. So since I mainly work on type 3 factors, so I don't really need to distinguish these two. Right. So, yeah. So, are there any questions up to here? Is everything clear? Good. So now, I should talk about the basic construction.
Where can one see a proof of that, right?
Oh, this one?
Yeah.
I think, well, in the case of two factors, then it's a Pym-Snapova.
Yeah, no. Simple system.
Simple system algebra, that's my own result.
Yeah, but where can one see that?
It appears in Credit Journal, yes.
So Pym-Snapova uses this semi-continuity argument, upper semi-continuity, signal or something.
Yeah.
What do you use for?
Actually, there is a paper of French people, 3 French people.
Oh, you're right.
Yeah. They treated a general von Neumann algebra case. So then I use the second dual argument. Yeah.
So any relation with the CV norm?
Sorry, CV norm?
Completely bounded norm.
I think the positivity is crucial here. Right, so Bon already talked about basic construction. Since it's very important, and this is the first lecture of mine, so I keep at least this lecture very elementary, so I start with basic construction. I mean, I'll give you the details of basic construction for the general case. All right. So the situation is this. So I already assumed this situation. There is a conditional expectation and also basis. So before you enter this room, I said that if you're here, then it's not. You might say that it's not fair to assume the existence of basis at the beginning. But once you assume the existence of basis, then I don't really need to talk about Tomita-Takisaki theory at all. So everything is algebraic once you assume the existence of basis. So, today still I'm in the C-star algebra setting. So okay. The basic idea is of course the same as Bon already told this morning, yesterday. But okay, I'll give you the detail. So since A is right B module. Okay, so I use a different notation for A as a right B module. And I also use this. So for element, well, just to avoid the confusion, so I use a different notation for A. This is not only A module, but it's so-called the Hilbert A module. Namely, so there's a nice B-valued inner product. So you can introduce a B-valued inner product this way. So this is a B-value inner product. So it looks like an ordinary inner product, but this is not a scalar. It's in B. And the Pimsner-Popper inequality shows that we have this, well, it's the equivalence of norms. Yes. We have this inequality. This is nothing but the Pimsner-Popper inequality. So this shows that as a Banach space, so okay, as a normal space, this is already a Banach space. So with respect to this norm, so this is a standard norm for Hilbert module. So this is a Banach space. And so, well, and this is so-called, what's so-called Hilbert Hilbert B module, Hilbert system module. And there is a nice theory about the Hilbert system modules. Namely, so you can consider kind of bounded operators of, say, B, okay, bounded operator with an adjoint operator. Then you get a sister algebra. So let me define this space, this algebra. So this is a set of T. Yes, okay. T is a bounded operator on this Banach space, such that there exists some bounded operator T star. It's adjoint. Such that, right, T star A1, A2 is equal to, well, I didn't put E here, sorry. It's confusing. I should put it here. Okay, this is not. So this is the so-called set of adjointable operators. And actually, this condition automatically assures that T is a right B module map, automatically. So any element here is a right B module map. And there is a nice theory about Hilbert system module. It says that this is again a C-star algebra, automatically nice C-star algebra. And in our situation, when we start with von Neumann algebra, then actually this is a von Neumann algebra structure automatically. It's called self-dual double-star module or something. So,
What is the name for self-dual?
the W star module. I think Pashke introduced it. Yeah. Right. Then, as I already told you, so there is a natural, obvious inclusion here. Namely by left multiplication. And also, so the conditional expectation E itself belongs here, but I don't want to use well, I want to use this notation for the conditional expectation. This is so-called Jones projection. Right. So, and they satisfy the obvious relation here. So this is a very easy computation. Right. And well, I erased the definition of basis, but the definition of the basis I introduced is nothing but the following equation. So we actually have this equality. So this is nothing but writing in a different way of the definition of the basis property. So if you apply the left-hand side to, say, eta A, then you immediately see that it's identity. Yeah. Right. And actually, so it's really nice to have this equation. So this gives you everything. So everything is algebraic due to this equation. So, and the most important statement along this line is that so let's call this. So this is a bit complicated. So let's call this A1. Then the point of the basic construction is that this is nothing but, so this is, well, since I use the theory of C-star, it looks like analysis is involved, but it's not the fact. It's not really the case. So this is determined algebraically. So I'm going to show this. This is a really important property. So it's at least as a linear space of, say, A bimodules, then this is nothing but the module tensor product over B. So I think my goal today is to show this. And then once you get that, then you get a dual conditional expectation automatically, well, almost automatically.
A is Hilbert bimodule or what is it? That is the equality of Hilbert B module. A is.
I'll show you the real meaning of this, but yeah. Okay. So, again, I'll show you a very easy computation. So for any t in A1, we have this following expression. So t can be expressed as this. Say ti, ui or ur star, where Ti is determined by this relation. Yes. So since you don't really need to take completion or anything, so this is other set. Then our Hilbert module is just 8 cells, so it makes sense, right? Well, this is really easy. Well, you just compute this. Okay. Then using the base property and so on, right? Yeah. This is probably the other way is much more easy. So let's start. Let's compute this. Then what you do is you expand A by using the module property, basis property. Yes. And since, this is a right B module, and T is a right B module map. So you have this. Say, all right. And yes, you can make this, right? Because T is a right module map, right B module map. Then what you get is that, say, Ti. And this is nothing but, yes, Ui star. Applied to eta A. Okay. Yeah. So this equality shows that T is nothing but this element. Right. So having this lemma, then I can make sense of this equality. So there are two natural maps here. So let's consider this. Okay, just algebraic B module tensor products. Then by using the universality of the tensor product, we have the following map. Since the Jones projection commute with B, any element of B, and by using the universality of the tensor product, we have a linear map here. Okay. Actually, it's a bimodule map. Right. And what I meant here is that this map is linear isomorphism. And namely, the inverse is given by this formula. Precisely. So given T in A1, then what you consider is the following. Ti tensor B Ui. So this is an element of A tensor A. And the theorem says that. So this is an isomorphism, linear isomorphism. With, this very explicit inverse. Actually, we've already seen the one direction of the proof. which one? So this is so starting from T, you go here.
UI.
Sorry?
The right side is UI star.
UI star, yes. UI star. Right, so starting from T, so you send T by this map here. Then you send by phi. Then what you get is this, right? So this is the identity. This is already done. And I think the other direction is also easy. So you start with an element like this, and then yeah, it's just a few line computations I omitted. Right. So this means that the basic construction is, well, nothing but just a module tensor product over B. So the universality of the module tensor product, then now we can introduce a dual, say, operator valued weight. Well, first you have to go through the operator valued weight, then using that, then we can introduce a dual conditional expectation. So, so using this result, so definition, we can introduce this map. So starting from A, the map from A1 to A, which sends X, E, Y to XY. And this is so-called a dual operator valued weight in the literature, in the type 3 subfactor literature. And this is well defined because A1 is an isomorphic to module tensor product. Right. And actually, the Kosaki's idea is that, okay, if you compute this, then you know that this is 1, UI, E, UI star. This is 1. And then by definition, you get this. And this is our definition of the index of E. So the real story about the subfactors of type 3 factors is the following. So this dual operator valued weight was constructed essentially by Hagelab theory of the operator valued weight with, say, J operator. Then Kosaki noticed that in the case of type 2-1 factors, then this number is nothing but, well, as you can see, the index of the subfactor. So Kosaki's approach is that, well, let's take this as a definition of the index. Then starting from this formula, he developed the theory of subfactors, of type 3 factors. That's what Kosaki did. So starting from the fact that this is finite, then you can show that there exists a basis and so on, so basic extension and so on. So that's what Kosaki did. But now I reversed order. So from the beginning, I assumed the existence of basis. Then now this becomes a theorem. Right. So, but this is not a conditional expectation. It's not normalized. So you want to normalize it and to get conditional expectation. And actually, it's possible. But for that, I should remind this. So this is actually a positive map. Yes. Well, this is positive. So since it's, well, once you know that it's positive, then you automatically know that it's bounded. Right? The norm is bounded by, norm of E hat is bounded by this element. The norm of this element. Actually, from the definition, it's not at all clear whether this is positive or not. Right? So you need to show something. And actually, so what we show is that, well, not only this is positive, but we show that this is positive. And it's enough. So we show this. And okay, every element, yes, yeah, that should be easy. Right. So every element x in A1 have the following expression. Oh yes. That's what we've already seen. So let's consider this. Then this is ij, xi, yi, yes, yi star. Sorry, yj star, e, xj star. And well, we use almost the same trick as before. When we show that Pearson-Popper inequality. So let's consider this part. Then, well, as a matrix, this is a positive matrix. And since this belongs to B, so it commutes with this projection. So as a matrix, we have this inequality. So let's put E here. We have this inequality as a matrix. In this algebra, Mn, so this is A1. Yes. You see? So this is a positive element, and E is a projection commuting with a positive element. So we have this inequality. So using this fact, then we get, yes. We get x star is dominated by ij and yes, xi, yj star, xj star. And this is nothing but E hat x star. So, well, from the definition of this map, it's not clear that whether this is positive or not is clear. But by using this simply computation, you see that it's positive. So, definition: the dual conditional expectation. So since the dual operator value the weight is not normal, so we can normalize it. Then it's clear that, well, already here it's clear that E hat is a bimodular map. And since this index is a central element, so this is still a bimodular map. And we saw that E hat is a positive map. So this is like E1 is also positive, and thanks to this normalization, this is unitary. So E1 is a conditional expectation. And this is called a dual conditional expectation. I still have 20 minutes. Okay. It's more than enough. Then the natural question is that so we started from the existence of a basis of E. So then we constructed we show that there is a nice theory of the basic construction. We get a dual conditional expectation. So the natural question is whether this is of index finite type or not. So can you guess the right formula for the index? The basis of E1. It's very easy exercise. And in fact, it's easy computation. Actually, which I don't really remember. So I have to cheat, but anyway. So okay, this is the right formula. This is the basis. Basis for the dual conditional expectation E1. It's easy computation. But this shows that, so when this is in general this is a central element, but when it is a scalar, this is a scalar. Then the index of the dual conditional expectation is again the same as let's compute it. Ui. So since we assume that this is a scalar, so you can pull it out here. Ui is E, Ui star. And this shows that it's the same as the index of E. Okay. So we get same index for the dual conditional expectation. Right. So is there any question up to here? So starting from the existence of basis, then everything is fine for sister algebras. But of course, what you are interested in is the case of von Neumann algebra. So let me briefly explain how this construction is related to the case of the one in the von Neumann algebra. So let's assume A and B are von Neumann algebras. Then usually you assume that E is a normal conditional expectation, meaning that it is a right continuity property with some topology, say sigma weak topology more precisely. Actually, it follows from the Pym-Snapper inequality, but anyway, let's assume it. Then for basic construction, what you usually do is the following. So you fix one faithful normal state. Okay. Then you extend it by using E. So this is the faithful normal state of A. And yes, then you consider the GNS representation. And to perform the basic construction for von Neumann algebras, then the usual definition is the following. So A, by using a GNS construction, so you represent A in this Hilbert space. Then what you do is that, right? Let's use this notation. You define the Jones projection this way. And the basic construction is by definition, say, okay, let's use this notation. See. So by definition, it's okay. Weak closure of A, say pi A. The von Neumann algebra generated by this set. And well, it's easy to see that this is nothing but the weak closure of this space. Right. But the point is that, in fact, well, you don't really need to take a weak closure here. The reason is the following. Well, you can repeat the same argument as I did by using a basis. That's one way, but well, actually it follows from the following computation. So, okay. Once you have a Hilbert B module, then you consider this tensor product. Then you take the closure. Well, there is a natural inner product in this linear space. Then you take closure, then you get a Hilbert space. And this is naturally identified with the GNS space of psi. And the identification is given by this map. Okay. Say you identify this vector with the GNS vector, cyclic vector of psi. Then this identification makes actually two Hilbert spaces are naturally identified. So on the left-hand side, there's a natural representation, A1 to B of. And under this identification, then this is identified with B of H psi. And it's easy to see that. Well, so this actually pi comes from this the action of A1 on this left tensor component. So there's a natural action here. Then you can easily see that you can identify this with the GNS. Okay, the restriction pi to A1, pi to A is nothing but a GNS representation under this identification, and the image of this projection is nothing but a Jones projection in that sense. And moreover, you can see that, first of all, so, well, to see that this is already, okay, to see that this is this space is already a von Neumann algebra, that space without taking weak closure is von Neumann algebra. Actually, it's enough to show that, this is already a von Neumann algebra. But it's obvious because of this identification. Okay. From this identification, then the image of B is already a von Neumann algebra. Then, let's see. So this is M1. So M1 is, since we have this, okay. Suppress pi. Let's suppress pi. Okay. Let me write this way. So this is, we know that this is 1. So you just then this is ui e m1 e J star. But from here, from this equation, this definition. So you already know that in this level, at first point, of course, you have to take a weak closure. But since we know that this is just already a von Neumann algebra, so you don't really need to take a weak closure. So it means that it is in A1. So this is already, so A1 is already a von Neumann algebra. So everything is algebraic. So
you need that first term because of the sum being equal to 1.
To take care of that.
Huh? It is enough to only take AEA. You don't need A plus AEA.
Yeah, in the end, you see that you don't really need this component. But yes, from this definition, then a priori you need this term. But this fact, so since this is 1, so you don't really need that term. Yes. Right. So I have 10 minutes left. Yeah. I need one really important technical result called the push-down lemma, and it will appear everywhere, almost everywhere in my next talks. Yes, I guess talk. So let me state that lemma. Push-down lemma. So the situation is as before. So we have a pair of sister algebras with a conditional expectation and a basis. So the push-down lemma says the following: for any element x in A1, there is a unique element y in A satisfying, so this form. Yes. This is so-called the push-down lemma of Pimsner-Popper. And actually, the point, so I think in the third talk, I'll present the sector theory in this setting. And well, you might think that you really need a whole type 3 theory to talk about the sectors and so on and so on. But it's not really necessary. The only point is this push-down lemma. I'll show that. To develop the type of sector theory for type 3 factors, the only point is the push-down lemma and the fact that any two non-zero projections are equivalent. That's all. So you don't really need Tomita-Takisaki theory and so on. That's why I'm doing everything algebraically today. And the proof is easy, really easy, because, well, for the uniqueness, once you have this equation, once you have this inequality, then you apply the dual conditional expectation. You get this, so this shows y. If there is such y, then y should be of this form. So this is a uniqueness part. And the equidistance part is also, since we have a basis, so also easy, because well, x can be expressed as the following. X say AI, CI, is in A. Yes?
You're still in the C-star algebra situation?
Yeah, C-star algebra.
So over 1 over index, you just win the inverse with central element.
Yeah. Okay, yes, it's inverse of central element, but it's larger than 1. It's invertible. So x can be expressed in this form. So this product is AI, yes, PI, E. So this shows that, yes, so this part is y. So this is a push-down lemma. And I'll use it in a crucial way. So I have 5 minutes left. So I'll talk about what I am going to. So tomorrow, tomorrow I will not give a talk. Day after, okay. So I'll say a few words about what I will do next time. So today I show that well, starting from a conditional expectation with a basis, then there is a very nice theory of index and basic construction and so on and so on. But in the case of a type 2 factor, there is a canonical conditional expectation, which is a trace preserving one. But in general, there is no canonical conditional expectation in that sense. But say in the case of factors, say when A and B are factors, or let's say when A and B are simple sister algebras, there is also a canonical conditional expectation in a different sense, which is called the minimal conditional expectation. So the index really depends on the choice of conditional expectation, but there is a very special one which minimizes all the possible values of index. That's a minimal conditional expectation. But unfortunately, well, even in the case of a type 2 factor, the minimal conditional expectation does not coincide with a trace preserving one in a very strange situation. More precisely, in the case where the inclusion, the subfactor is not extremal, which Bond didn't talk about, then the two conditional expectations do not really coincide. And well, I guess there is a discussion about which is the better conditional expectation in that situation. Well, I should say that well, non-extremal inclusions are really strange ones. So we don't need to decide which is better. But there is a point. There is a point which I really want to stick to the minimal conditional expectation. Namely, the reason is the following. So it's a program versus index. Say index and say dimension, square root of index. So this is a as you saw in an example, this is a quantity something like the cardinality of the group, finite group. But on the other hand, this is the square root of the index is how to say, it's something like a dimension. So if you look at say Wassermann type subfactor, well, which well probably I'll talk about at some more point, then this corresponds to the dimension of the representation. So, well, I guess Bohm believes that this is more natural than the other one. But I believe that this is better. This somehow behaves better. And
one is always a cyclotomic integer and the other one isn't.
right, that's also right. But the point is that, okay, tomorrow I show that, when this inclusion is not irreducible, so it's not. So the relative commutant is not a scalar. Then you want to compute the local index, namely, so you take a say partition of unity consisting of minimal projections. Pi minimal projections. Then you want to compute the index of this. So this is so-called local index. So it turns out that this quantity behaves well. I mean, for local index, then the square root is better. The reason is that, so if you use minimal conditional expectation to define the index of subfactor, then you have this additivity property for the square root of the index. And index doesn't have this additivity property.
On the right, you mean the minimal index?
Yeah, for the minimal index, yes, this is the case.
So on the left, they're automatically minimal.
But yeah, so in my definitions, this index is defined in terms of minimal conditional expectation. For the minimal conditional expectation, then you have this additive property for the dimension, I mean, square root of the index. So
But on the left, it's the ordinary index anyway. They're reducible.
yeah. Okay, I stop here.